All right, here we go, trying out the Waterloo method. I'm going to, on this first page, page 1 here, these are all just direct basic unit conversions, sometimes with compound units. But the real power of the Waterloo method is using unit conversions inside calculations, so that you do the calculation and the unit conversions all in one big step. You end up banging a bunch of numbers through your calculator that's all just multiplications and divisions and maybe the odd square. But there's no brackets really required. So the idea is you can do these calculations robustly and reliably without making common unit conversion errors. So we're just trying to convert all of these quantities to base units, either US or metric base units as appropriate. First one there, 12.5 bar. Well, a bar is a metric unit of pressure. It's equal to 100,000 pascals, 100 kilopascals, which is a handy unit only because it's pretty close to being an atmosphere, about 1 atmosphere. A bar is really close to 1 atmosphere, which is 101,000 pascals. So the way that we write it is this. I'll zoom in a bit here. So you start off by putting the quantity on here, 12.5 bar, and everything in the Waterloo method is something over something. So it's just 12.5 bar. What would that be over? Well, just over 1 then. And then we draw these vertical lines to separate our quantities. And now we're going to multiply by a unit conversion. We need to know the conversion from bars to the base unit, which is pascals. I just said it's 100,000 pascals. So I'm going to put 1 bar on the bottom here and 100,000 pascals on the top. I could have put 1 bar on the top and 100,000 pascals on the bottom, but that wouldn't help. I want this bar on the bottom to cancel this bar on top. When I do that, what I'm left with is just pascals. Notice this entire quantity here. That's an odd form of the number 1. 100,000 pascals, that's a quantity of pressure, divided by another quantity of pressure, 1 bar. But the thing is, those two things are equal to each other. They're the same pressure. When you divide one quantity by another identical quantity, you get just the number 1. Not 1 anything, not 1 pascal, 1 bar, just 1. Nice thing about 1 is you can multiply anything by 1 and you don't actually change that quantity. But in this case, you fix the units. So what we're left with is 12.5 times 100,000. Works out to be simply 1,250,000 pascals. You might also say 1.25 megapascals or 1,250 kilopascals, but nobody asked about that. They wanted it in base units, which is pascals. Similar to the next one, 15 megapascals, so okay, 15 megapascals over 1 times the unit conversion that gets rid of the unwanted unit, megapascals. 1 megapascal is 10 to the power of 6, or 1,000,000 pascals. So the units cancel out. I'm left with just pascals. So it's 15 times 10 to the power of 6 pascals. 35 minutes. Well, minutes is fine, but the base unit is seconds. So it's 35 minutes, I guess, over 1, times the unit conversion with 1 minute, or some quantity of minutes on the bottom, and 60 seconds, the equivalent time on top. Minutes cancel. So what you bang through your calculator is 35 times 60 divided by 1 if you must, but you can leave out the ones. It's just 35 times 60, which is 2,100 seconds. $45 kilowatts, well, that's a unit of power. I want it in just watts, though. Multiply it by 1 kilowatt, and the equivalent in the units you want is 1,000 watts. Kilowatts cancel, you're left with just watts. 45 times 1,000 sounds like 45,000 watts. 15 megajoules, it's a unit of work or energy or heat or something like that. So 15 megajoules over 1, and then 1 megajoule is the same thing as a million joules. So it's just 15 million joules. Or if you wanted 15 with 6 zeros. The question didn't specify the number format for the final answer, so this engineering notation or scientific notation or just full-on decimal notation, any of those would be fine. 15 kips. Kip is an odd unit. It's a kilopound, 1,000 pounds. A little strange that you would use kilo with pounds, because kilo is usually a metric thing and pounds is a US thing. We don't talk about mega feet and milli inches so much, but a kip is a handy unit, so we use it conventionally in engineering. So 15 kips over 1, that's just the original quantity. The 1's just a placeholder, really. You don't have to put it if you don't want to. And 1 kip is the same thing as 1,000 pounds force. Kips cancel, so it's just 15,000 pounds force. 22 GPM is a little trickier with this one, because a GPM, writing it, just GPM with those letters, that's sort of a convention. But when you're doing math with it, you really want to do it explicitly as 22 gallons over every single minute. That's what that quantity really is explicitly. I don't want gallons, I don't want minutes. Gallons? No, that's a US unit of volume, but the base unit of volume would be cubic inches. Minute is, of course, a unit of time, but the base unit is in seconds. So I want to get rid of both gallons and minutes, and it doesn't matter which one you start with. I'm going to get rid of a minute, because 1 minute is the same thing as 60 seconds. That cancels out minutes. So if I take 22 divided by 60, that's some number of gallons per second. Progressive of sort, but I didn't want gallons, I want cubic inches. I happen to know, because this isn't my first rodeo, that 1 gallon is 231 cubic inches. Maybe that's not a familiar unit conversion to you. It probably will be as we work through the course. You probably know about seconds to minutes and feet to inches and meters to millimeters and stuff, but we'll learn a few more as we go along. Otherwise, this 1 gallon equals 231 cubic inches. That's the sort of thing you'd look up in the back of the book, or probably page 4 of this very document. Gallons cancel. And the only units I'm left with now is cubic inches per second. That's what I wanted. So these two multiplications of something over something, a minute over 60 seconds, 231 cubic inches over 1 gallon, those are basically just multiplying the original quantity by a fancy version of 1 and another fancy version of 1, but with the units such that they cancel out in a useful way. So what I bang through my calculator is 22 times 1 times 231 divided by 1 divided by 60 divided by 1 again, with no brackets. And frankly, you can just leave out the 1s, of course. So it's really 22 times 231 divided by 60. That's the number. What about the units? Well, the units are what's left, cubic inches per second. So the number works out to be, 84.7. That's 22 times 231 over 60. And the unit is cubic inches per second. And there's our answer. Similar thing with Q pump is 120 liters per minute. We pretty commonly use Q as the flow variable or symbol. LPM is liters per minute. Again, a conventional notation, but it means 120 liters every single minute. I don't want liters. I don't want minutes. 1 minute is 60 seconds. That's my conversion from minutes to seconds. Minutes cancel. I want to get rid of liters and replace them with cubic meters. A liter is certainly, it looks like it might be the base unit of volume, but it's a derived unit, right? A liter is a volume, which is a distance times a distance times a distance. So the base unit we want is cubic meters. I want to get rid of liters. This L is on the top, so on the bottom, I want to know about liters. Well, there's 1,000 liters in 1 cubic meter. Again, I just happen to know that. Now you do too. That liter cancels with that liter. And I'm left with cubic meters over seconds. Just base units is what I wanted. So what you bang through your calculator is 120 divided by 60 divided by 1,000. Again, no brackets. You get the number, and the number is 0.002, quite a small number, cubic meters per second. Actually, this 0.002, that looks like it's only one significant digit. It is. You can throw a couple more zeros in there if you wanted to, because it really works out to bang on 0.002. I guess just a word about flows in metric units. We kind of want base units. Trouble is, a cubic meter, that's a pretty big volume. You know, a box 1 meter by 1 meter by 1 meter, if it's hydraulic oil, that's a pretty big box of oil. If that's the flow, if one of those is flowing every second, that's a lot of flow. You know, whole numbers of cubic meters per second, that's the kind of flow you get in rivers, not so much hydraulic pipes. So you got to get used to the idea that when you're dealing with flows in hydraulic systems in metric, in base units, cubic meters per second, the actual number tends to be a really, really small number, which is fine, except it's a little bit problematic because 0.002, I don't have a really good feel for what that looks like. You know, if there's one extra zero before the 2, I might not notice. 84.7 cubic inches per second up above, I kind of know what a cubic inch looks like, and I know how long a second is, and so 84.7 cubic inches, I can kind of imagine that in my mind. What you know, that's not exactly, but you know, that's I don't know, that's probably close to a liter or something like that, right? It's not a huge volume. It's not a little tiny volume. It's kind of volume that you might hold in your hand in some sort of a bottle. 84.7 cubic inches every second. So unfortunately, this metric version of flow in base units is a little bit not very intuitive or friendly, but there it is. 20 feet per second. Well, okay, I don't want feet. So 20 feet over 1 second. I just want to replace feet with inches. So the foot goes on the bottom so as to cancel, and the equivalent distance of 12 inches goes on top, and I've got 20 times 12 inches per second. 240, I think. "15 miles per hour. Again, the miles per hour is a conventional form, mph, but it really means 15 miles over 1 hour. I want to get rid of, well, miles and hours. I want inches and seconds. The hours isn't a big problem. I know an hour is 60 minutes, and 60 minutes is 60 seconds is 1 minute. But I also just happen to know, because I've done this before, 1 hour is directly 3,600 seconds. I don't need to do that in 2 steps. A mile, though, I don't know how many inches are in a mile. Could look it up, could Google it, ask MathCAD. But I don't know offhand. What I do know, though, is that 1 mile, and I just happen to know it's 5,280 feet. I just remember that. Gets rid of miles, which is helpful. Replaces it with feet. I didn't want feet, but I know how to convert feet to inches. 1 foot is 12 inches. So what I'm going to bang through my calculator is 15 times 5280 times 12 divided by 3600, and the units I'm going to be left with when I'm done canceling is inches per second, just what I wanted. That's 264 inches per second. And finally, the 35 kilometers an hour. Same sort of thing. It means 35 kilometers divided by 1 hour. What's that in base units? Well, a kilometer is 1,000 meters. An hour is 3,600 seconds. Hours, gone. Kilometers, gone. Meters per second remain. 9.722 meters per second. All right, so I said that those were just unit conversions using the Waterloo method. And really, part of the Waterloo method is because you're multiplying by something over something, it prevents you from making the really common mistake when you're doing especially unfamiliar unit conversions. If you know the unit conversion between feet and inches is the number 12, okay, I want to convert feet to inches. 12, eh? Do you multiply by 12 or divide by 12? Easy to screw that up. The Waterloo method prevents you from making that mistake because you arrange that fraction, that something over something, in the way that gets rid of the unit that you're trying to get rid of. So, problem one, actually the first engineering problem, which involves a fairly simple basic equation with some messy units and quantities. So we just want to know how fast you're running on average if you do a half marathon in 3.5 hours or 3.15 hours. The distance is 21.0975 kilometers. I looked it up. 3.15 hours, that's not bad going. So the basic equation that relates these things is velocity is distance over time. I know the distance, 21 kilometers. I know the time, 3 and a bit hours. If you just divide those out, though, the answer is going to be in kilometers per hour, and you're looking for meters per second. So what we're doing is the Waterloo method. So you write out the equation, and distance and time, put in the distance and time, and then start applying the conversion factors. Get rid of kilometers, because 1 kilometer is 1,000 meters. The kilometers are gone. Get rid of hours, because 1 hour is 60 minutes. Again, let's get rid of hours. But now I've got minutes. I'll get rid of the minutes by putting 1 minute over 60 seconds. That minute cancels that minute. The only thing you're left with is seconds on the bottom and meters on the top, meters per second. What you actually could put through your calculator then is, again, without brackets, just the number part, all the stuff on the top multiplied, divided by each of the things on the bottom. So 21 times 1,000 times 1 times 1, divided by 3.15, divided by 1, divided by 60, divided by 60 again. No brackets. Prevents you from making that common mismatched bracket error. Of course, you don't need to multiply by 1 and divide by 1. It doesn't do anything. So practically, what you just put through your calculator is all those non-1 values shown in the bottom here. You get the same number, and the units are whatever units you had left here, meters per second. So here's a really nasty version of this problem. It's how many microseconds does it take? So we're looking for a time, looking for how long it takes to do a trip. We're in a starship doing a half a light year every fortnight. 0.5 light years per fortnight, that's a really weird way to express velocity, but it's fair enough. It's a number of a distance over a time. You can do that, right? Kilometers per hour, yards per second, feet per day, whatever. This is what we were given, slightly obnoxiously, but there we are. And the distance we're traveling is, well, it could be some number of inches or miles or light years or kilometers, but it's smoots. That blue thing's a hyperlink. If you click it, it'll tell you what a smoot is and what's the deal with smoots. It's an odd unit of distance equal to about 1.7 meters. It's actually the height of a guy named Smoot. Anyway, so we have a velocity and a distance. We want to know how long it takes in, oddly, microseconds. So the basic equation is still velocity is distance over time, but we got to solve it for the variable we're after, the time. There's the working equation. Time, the time that we're after, is equal to the distance we're given divided by the velocity we're given. Okay, so here's how you do it. The time, I gotta get a little small here. This is going to take up a bit of space. It's the distance over the velocity. Well, the distance is 50,000 smoots. What's on the bottom, though? The velocity. We're dividing by velocity. So I treat it as a separate quantity. I'm going to take the distance part, and it's its own thing. There's a little placeholder there. To divide by velocity is the same thing as to multiply by the inverse of velocity. So since velocity is on the bottom, You put it in as something over something, but it's the upside down version of it. What it is, it's 0.5 light years. So the 0.5 light years goes on the bottom, and the fortnight goes on the top. I'm just going to make up a symbol for a fortnight. So if you were to multiply by the velocity, you'd put 0.5 light years on the top and the fortnight on the bottom. We're dividing by velocity. So you take the 0.5 light years per fortnight and you flip it upside down into fortnight per 0.5 light years, so to speak. That's a major part of or a little trick, I guess, in the Waterloo method. So basically, I gotta get rid of a lot of units here. I don't want smoots. I don't want anything, actually. I want a time unit. But look, there's smoots on top, distance unit, light years on the bottom, also a distance unit. They will cancel. I want to convert both smoots and light years to the same thing, say meters, and then they'll cancel out. So, and I want to get rid of fortnight and replace it with microseconds eventually. You don't have to do it all in one step, though. You can do it in multiple steps. One smoot is given as 1.7018 meters. Smoots are gone. A light year, I'm going to get rid of a light year as well. 1 light year is given as a big number of kilometers, 9.460528 not meters, times 10 to the power of 12, kilometers, 9.4 trillion kilometers. That light year cancels this light year. I got meters on top here, kilometers on the bottom. They almost cancel, but they're both a distance, but they're not the same unit. So I'm gonna get rid of kilometers. Say 1 kilometer is 1,000 meters. Kilometers are gone now. And look, this meter cancels out this meter. What units am I left with? Only fortnights, only the time unit. That's all that remains. Well, okay, good. If I bang this numbers out, if I take 50,000 times 1.7018 divided by 0.5 divided by 9.46E12 divided by that, do all that, you'll get a number. It'll be a number in fortnights. I wanted it in microseconds. Kind of running out of space here. So I guess I'm going to do this multi-line thingy here. Carry on. I still want to get rid of fortnights. Fortnights is on the top, so I want to put a fortnight on the bottom with its equivalent, ideally in microseconds, but I don't know how many microseconds are in a fortnight. I do know there's 2 weeks in a fortnight. That gets rid of fortnight. And I know that 1 week is 7 days. That gets rid of weeks and replaces it with days. And I know that a day is 24 hours. I happen to know an hour is 3,600 seconds. I didn't want seconds, I wanted microseconds. 1 second is the same thing as 1,000,000 microseconds. So seconds are gone, hours are gone, days are gone. Everything's gone. The only thing remaining, all of these units cancel out. The only thing left is microseconds. Just what I wanted. So again, bang through this with your calculator. Only in one step. This is the first time you'd pick up your calculator in this problem. 50,000 times 1.7018 times 2 times 7 times 24 times 3,600 times 10 to the power of 6 divided by 0.5 divided by this 9.46E12 divided by 1,000. All the rest are ones. So that's the number. And when you bang out all of that through your calculator, the number is 21.8, and the units remaining are microseconds. That's a mu. And that's micro symbol. There's your answer. If you're traveling at the actually insanely and unreasonably fast speed of a half a light year every fortnight, well, you can't. That's faster than the speed of light by a fair bit. But if you were, and you had to cover 50,000 smoots, it'd take you 21.8 microseconds to do it. Okay, this is the sort of thing that the Waterloo method really, really excels at. This problem has a lot of unfamiliar, frankly obnoxious units, but the actual math is just time is distance over velocity, right? If the distance was 2 meters and the velocity was 2 meters per second, the answer would be 1 second. It's pretty straightforward mathematically, but the unit conversion is what makes this tricky. Really easy to confuse these unfamiliar unit conversions and mess them up. But the Waterloo method guides you so that you always know if you're multiplying or dividing by the conversion factor, essentially. Let's see, number 3 there, what's the inside area in square inches of a pipe? The inside diameter is 20 millimeters. Well, okay, the basic equation is area is pi by 4 d squared. That's what we're after. Area, it's pi over 4 times the d diameter term squared. When we do the substitution, the pi by 4 stays the same. The diameter is 20 millimeters, but it's squared. There's 2 ways you can do this. You could just do this. That's right, but it's not all that helpful. I'm going to do it in a slightly different form. It's 20 millimeters all squared. That means the number part squared and the unit part squared. You just do it like that. I don't want millimeters. I want inches squared. So I got to get rid of the square millimeters. I need to know, how do you convert from millimeters to inches? Well, I was given that 25.4 millimeters is 1 inch. But I'm dealing with square terms. So here's what I do. You square everything. 25.4 millimeters, that's squared, and that's squared, and that's squared, and that's squared. So if there's 1 inch in 25.4 millimeters, there's 1 squared inch squared in 25.4 squared square millimeters, so to speak. So these square millimeters cancel those square millimeters. I'm left with just square inches. That's what I wanted. So in my calculator, I'm going to put in pi times 20 times 20, never mind the times 1, divided by 4, divided by 25.4, divided by 25.4 again. That's the number part. Or you could have just put in pi times 20 and squared it, divided by 4, divided by 25.4 and square that. And same thing. And the units in both of these versions was square inches. So we're going to get 0.487 square inches. You know, it's a really good idea to do a sanity check when you can. This Starship, Smoots, Light Years, Fortnite thing, that's pretty weird. We don't have a really good conception of it, but I kind of know what something round that's 20 millimeters across, kind of know what that looks like, right? That's about, oh, it's not far off the size of my thumb. I'm looking for, in this problem, essentially something quite a lot like, what's the square inches area of my thumb? I look at my thumb and think about chopping it off and looking at what's left. It makes me a little uncomfortable thinking that way. But what's left would be a bloody circle about literally, physically, about that big. How many square inches is that? I don't know. It looks like less than a square inch to me. It's certainly not 50 square inches. It's certainly not 0.003 square inches. Something like a half a square inch? The answer is something like half a square inch. Seems like that's about right. This sort of sanity check that you can do is really, really expected. Strongly recommended, frankly expected as you progress through this whole program. You can be wrong, but you can be way wrong. You can be crazy wrong. This number seems reasonable. It doesn't guarantee that you're right, but if you get a number that's really, it can't possibly be, right? The cross-sectional area of my thumb is not 5,000 square inches. If I get the answer 5,000 square inches, you really want to pause and look at that and consider what it means. Put it in some mental context. And if it seems unreasonable, go look for what went wrong. I will not give you questions with crazy, made-up, silly values. They'll always be more or less practical, more or less reasonable, and your answers should therefore be more or less reasonable. Last one on this page, similar to what we just did. I want to know the inside diameter, though, of a pipe given the area. So I still need the basic equation that relates area and diameter, but I need to rearrange it into a working equation. We call this a basic equation, the sort of thing you look up in a textbook, and we call this a working equation, the sort of thing you have to make yourself by rearranging the basic equation. It's pretty straightforward in this case. So diameter is what I'm after. I want it in millimeters. So the diameter, it's going to be 4 over pi times the area, but that all in a square root sign. And when you do the substitution, it's still just 4 over pi. It's still the square root. The area, though, is 0.23 inches squared. Notice I'm not squaring the 0.23, am I? It's 0.23 inches squared, not 0.23 squared. I'm not squaring the quantity, it's just the unit. So I want to get rid of square inches. Well, 1 inch is 25.4 millimeters from the previous problem. But this only gets rid of, this is only one conversion. This is inches. This is, on the top is square inches. So what I do is square, well, you could just square everything. You could make that squared, that squared, that squared, and that squared, and do it. Another way that you can think about it, though, that I kind of like, because it's so direct, is this. There's one conversion. That gets rid of one of the inches. You just do that again. 25.4 millimeters again over 1 inch. This inch and this inch together cancels the square inches. What I'm left with on the top is millimeters times millimeters. That's square millimeters. But it's the square root of square millimeters, which is just millimeters. So this works out to be, well, the square root of 4 times 0.23 times 25.4 times 25.4 again, divided by pi, and that's all for numbers. Square root of that, and also the square root of whatever units I've got, which is millimeters squared. The number part works out to 11.7, and the number part, square root of square millimeters, is just millimeters. So far, so good. All right, here's some that are a little more actually sort of hydraulic, less just about the Waterloo method, and now applying it to some basic problems. Some of this might be hopefully a little bit familiar from physics and just living your life. We want to, in any case, the basic equations are all given. So we want to calculate the work W usually, but in base units. If we want to lift a 1-ton load, a distance of 8 feet, I'm calling S the distance. It's for the stroke of a hydraulic cylinder is 8 feet. So this is kind of like lifting up a car about 8 feet. Maybe you're going to change the oil or something like that. How much work is done to lift that load? Well, the basic equation we need, work is force times distance. Okay, so when we do the Waterloo method, the work, it's the force times the distance, and the force is 1 ton of force. You could call it a tonf if you want. A ton force is equal to 2,000 pounds. Times the distance, which is 8 feet. I want this in base unit. Well, base units of work, well, work is force times distance. So the base unit is, we're in US units. So the US unit of force is not a ton of force, it's a pound. The US unit, base unit of distance is not feet, it's inches. So I want to get rid of tons, replace them with feet. Tons replaced with pounds. I want to take feet and replace it with inches. Okay, well, 1 ton of force is the same as 2,000 pounds of force. And 1 foot of distance is 12 inches of distance. So the feet cancel, the tons cancel. I'm left with inch pounds. You might not be familiar with this, but an inch pound is absolutely a unit of work. An inch times a pound, a distance and force multiplied together. So the number comes out as 192,000 inch pounds. Just as an aside, inch pounds. I'm claiming that inch pounds is a unit of work or force or energy or even heat. They're all kind of the same thing. And we're used to thinking about those things, at least in metric, as joules. A joule is the same as a Newton meter. It's a joule. In US, there isn't really this base unit. There's something called a BTU, but we're not going to bother with those. The base unit of work is just an inch pound. You go, wait a minute, inch pounds, isn't that torque? Isn't torque in inch pounds, foot pounds, like that? Don't you tighten up your lug nuts on your car to about 80 foot pounds? So what are we saying? Torque is the same thing as work? Same units? Does that mean it's the same thing? No. We'll leave it at that for the moment. It's a vector thing, fundamentally. It's 2 different vector kinds of quantities. One, the inch pounds when it's torque is a rotary vector. Inch pounds when it's work is not a vector. It's a scalar quantity. If that doesn't make any sense to you, don't even worry about it. Just know that inch pound is a base unit of work. It's also a base unit of torque, but the inch pounds are slightly different things. They have a slightly different meaning. Anyway, that's it. Similar problem in metric. We're going to need a unit conversion because this is both metric and US. Same kind of thing. Work is force times distance, which is 1.5 tons of force, apparently, times a distance of 2.5 meters. I want that in joules. I want it in joules in this case. That's what it says here. I want to know work W in joules. So I want the metric version of this. So I don't want tons. I don't want tons of force. I got to convert that to, well, the metric version of that, which is newtons. I know offhand, though, that 1 ton is 2,000 pounds of force. And I know how to convert pounds to newtons. I had to look it up, actually. But there is 4.448 newtons is 1 pound of force. So the pounds of force are gone. The tons of force are gone. I've now got Newton meters. Actually, I'm pretty happy with that because that's direct. 1 Newton meter is 1 joule. That's what a Newton meter is, or a joule is. It's 1 Newton times 1 meter. The joule is the amount of work when you push with 1 Newton through a distance of 1 meter. That Newton cancels that Newton, and that meter cancels that meter, and I'm only left with joules. So it's 33,360 joules, I believe. Number 7, good solid hydraulic problem. What's the speed of a fluid in a tube? If the area of the tube is given and the flow rate is given, give me the speed in base units. Well, we're in US units, so base unit of speed is inches per second. That's what I want. The equation is Q equals VA. I know the velocity. Oh, sorry. I don't know the velocity. I want the velocity. So I need to take this working equation. I need to take this basic equation and recast it. I want velocity, so my working equation is V is Q over A. Well, Q is 12 gallons every single minute. And A, which goes on the bottom, is 0.105 square inches. right? Dividing by A is the same thing as multiplying by 1 over A. That's what I've done here. If I just bang out these numbers, I'm going to get, I don't know, a little, about 120 or a little less. But the units would be gallons per minute inch squared. That's no way to talk about a velocity. I got to get rid of gallons and minutes. Well, 1 gallon is 231 cubic inches. The gallon's gone. As a matter of fact, the inches, look, I've got inches cubed on the top and square inches on the bottom. That leaves me with just inches on the top. But I've still got minutes on the bottom. 1 minute, 60 seconds. Minutes, gone. I've now got inches per second. Just what I wanted. That's 440 inches per second. Number 8, what's the pressure in pascals? Pressure, little p. In a hydraulic cylinder whose bore diameter, the inside diameter of the cylinder, is 3.5 inches. That's could be a size. And the applied force is 9.5 kilonewtons. Again, this is a little unfamiliar. We haven't got this far. We're going to get into this pretty soon in the lectures. But it doesn't really matter. It's just a problem. We're given some values. We're given the basic equation. P equals F over A. Oh, and A is pi d squared over 4. I want to know the pressure. I'm going to combine these to make a working equation that's P is, well, if it's F over A, isn't that F over pi d squared by 4? I don't like this fractions over fraction business, though. So I'm going to recast this as, well, the bottom is being divided, so it's equal to F times, well, 1 over A, so to speak. Or A to the negative 1, if you prefer. Or just take the A and flip it upside down. It's 4 over pi d squared. The pressure I'm looking at then, it's 4F over pi d squared. I've just really created my a working equation from these two basic equations and put them in a straightforward form of just something over something, not something over something over something, which gets confusing. Anyway, this is now algebraically what I want to evaluate with the Waterloo method. So P is 4 over pi, that could be its own thing, times F over d squared. So the 4 over pi doesn't change. The force is 9.5 kilonewtons. The diameter is 3.5 inches. Right? I've taken this fractional and little hash mark thing and converted it to conventional. And I want to know the pressure in pascals. Again, bit of a mess because this problem has inches, US units, and kilonewtons, which is metric. So I got to get rid of inches, replace them with meters, base units of metric distance. So what's my conversion there? Well, I know that 1 inch is 25.4 millimeters. That gets rid of inches. But I don't want millimeters, I want meters. There's 1,000 millimeters in 1 meter. That gets rid of millimeters. I've now got, oh sorry, it was d squared, wasn't it? It was 3, oh. Sorry, I screwed this up a bit. Let me fix this. Diameter squared, right? So that's 3.5 squared inches squared. I don't want inches. 1 inch is 25.4 millimeters. But I don't want inches, I want square inches. So you square everything. That square inch gets rid of that square inch. I don't even want millimeters. I want meters. I want a kilonewton, and I don't want kilonewtons. I want newtons per square meter. A newton per square meter, that is a Pascal. That's where I'm going with this. So let me see. There is 1,000 millimeters in 1 meter. That means there's 1,000 squared millimeters squared in 1 squared meter squared. There's 1,000,000 square millimeters in a meter. That's a good thing to keep in mind. People screw that up a lot and think there's 1,000 square millimeters in a square meter. Think about a square meter divided up into a grid of little 1 millimeter boxes, and there's 1,000 along one side and there's 1,000 along the other side, and the area is 1,000 squared. It's 1,000,000. If you ever want to know what 1,000,000 of something looks like, think of a square meter divided up into little boxes of millimeter size. The last thing is kilonewtons. I didn't want kilonewtons. 1 kilonewton is 1,000 newtons. Kilonewtons cancel. Square millimeters cancel. I'm left with newtons per square meter. That's what a Pascal is. I guess you could go one step further and say that 1 Pascal is the same thing as 1 Newton over a square meter. That's getting a little messy there. And it comes out to 1.53 times 10 to the power of 6 pascals. Number 9, convert the previous pressure into PSI and bar. Oh, well, okay. Let me see. 1.53, sometimes I just write E6 pascals over 1. If I want that in PSI, well, apparently 6895 pascals on the bottom is 1 PSI. Pascals cancel. And I'm going to get 15.3. 221.9. 221.9 PSI. If I want that in bar, okay, 221.9. I'm going to just go with PSI. I'm not going to write it as pounds per square inch. You could, but it's not necessary because I'm just dealing only with pressures in this problem. I'm not pressures and areas and forces. It's just pressures. That pressure is 14.5 PSI is 1 bar. Those cancel, and then that pressure works out to be 15.3 bar. Almost there. I've been at this for a while, Calculate the extend speed. How fast is a cylinder moving? If it has a bore area, if the inside area is 2,200 square millimeters, and the flow is 5 GPM into it, again, a bit of a mess of this US and metric problems combined. What's the speed? Well, the basic equation, again, not familiar to you. We'll talk about this in class, but there's the equation, the relationship between our 3 variables. We have flow, Q, velocity, V, and area, A. We want to know velocity, V. We were given Q and A. So there's our equation, Q over A. Q is 5 gallons every minute. A is on the bottom, divided by, so we put it on the bottom, it's 2,200 square millimeters. And I want the speed in meters per second. Oh boy. Well, I don't, so here's the thing. I don't want gallons or minutes or square millimeters. All those units have to go. I want meters and seconds. Okay, I'm going to, one at a time, and it doesn't matter what order you do this in. You've got to replace those obnoxious units that you don't want with units that are in the right direction. My final answer is going to be in meters per second in metric. So any distances should be in meters. Any areas should be in square meters. Any volume should be in cubic meters. I'm going to start with the gallons. 5 gallons. Well, how many cubic meters in a gallon? I could look that up, I guess. But I'm not gonna. I'm just gonna say I know that 1 gallon is 231 cubic inches. Gets rid of gallons. What about cubic inches? Well, I know that 1 inch is 25.4 millimeters. But I've got cubic inches here. I guess I'm cubing everything. Cubing that, and that, and that, and that. And these cubic inches cancel those cubic inches. Now let me see. I've got cubic millimeters on the top and square millimeters on the bottom. Those cancel, and it just left with millimeters on the top. Let me get rid of millimeters. There's 1,000 millimeters is 1 meter. Millimeters are now gone. Let me see what I've got. Meters on top, and that's it. And on the bottom is minutes. Oh, I'm getting there, eh? Meters per minute. I just want to get rid of the minutes. 1 minute is 60 seconds. That minute cancels that minute. Look what I got. Meters and seconds, and that's it. So through my calculator, I'm going to put 5 times 231 times 25.4 cubed. Don't forget that. That's an easy mistake to make. Times 1, but never mind that. Divided by 1, but never mind that. But divided by 2200. And then a bunch of ones. Divided by 1,000. Divided by 60. And the units remaining are meters per second. I think it works out to 0.1434 meters per second. Finally, one more. Calculate the power in horsepower to lift 2.5 tons at a speed of 8 feet per minute. Again, we're not familiar with this as an equation. I guess I better give you the basic equation. The basic equation for power, that's my fancy P for power, to distinguish it from pressure and stuff. Power is force times velocity. That's the basic equation. If you forgot that from physics, consider yourself reminded. But I want it in horsepower. I'm going to need a conversion for horsepower as well. Let's see what the base units give us first, though. Let's get this in base units and then put it in horsepower. Again, though, using the Waterloo method and all in one go. So the power is a force of 2.5 tons of force times a velocity of 8 feet every minute. And I want to get rid of one base units. Well, force times velocity. Force is pounds. Velocity is inches per second in US. So what I want for power is pounds times inches per second. Basically, inch-pounds per second. Again, that seems like an odd unit of power. You don't often hear power talked about as inch-pounds per second. You hear about horsepower. But I assure you, the base units of power in US is inch-pounds per second. In metric, it's Newton meters per second, which is also a joule per second, which is also a watt. So in metric, we have watts for power. It's a derived unit, but it's a friendly one. Horsepower is some messy number of inch-pounds per second. We'll get to that. Let's get rid of tons. 1 ton of force is 2,000 pounds of force. Get rid of feet. 1 foot is 12 inches. And 1 minute is 60 seconds. Minutes cancel. Tons cancel. Feet cancel. Look what I've got. Pounds, inches, seconds. Inch-pounds per second. That's good. That's fine. This is going to give me the answer in some number of inch-pounds per second, but I wanted horsepower. Okay, well, this is one of the trickier kinds of unit conversions because 1 horsepower, you can look it up. Somewhere it says that 1 horsepower equals some number of inch-pounds per second. I happen to know it's 6,600 inch-pounds per second. So I've got to form that into a fraction, as something over something. I want horsepower on the top. So what I'm going to do is this. I'm going to multiply by 1 horsepower. And what goes on the bottom is the 6,600 inch-pounds with seconds on the top. This whole thing is one unit conversion. It's kind of in two pieces. 1 horsepower on top, 6,600 inch-pounds per second, upside down or on the bottom. Look what happens here. Inches, gone. Pounds, gone. Seconds, gone. Only thing remaining is horsepower. So through my calculator, I put 2.5 times 8 times 2,000 times 12. That's it. Some ones remaining on the top. Divided by, well, a bunch of ones, but divided by 60. Divided by 6,600. And the units are horsepower. Comes out to 1.2 or so horsepower. If you want to lift something that weighs 2.5 tons, and you want to lift it at a speed of 8 feet per minute, you need yourself 1.2 horsepower to drive that system. If it's a hydraulic system, you need a pump that delivers at least 1.2 horsepower if you want to be able to lift that load at that speed or more. If you have less horsepower than that, you could still lift that load, but at a lower speed. Low power basically means low speed or low force, or both. On the last page is of unit conversions that might be handy for this course and you might have used through the course of this activity. And I hope this helps.